All right, so now we're going to talk about the ideal gas law. And again, this is a mathematical equation that was derived from that kinetic molecular theory, from those assumptions that we made about gases being really far apart, traveling in straight lines, and not really interacting with one another. How they got this equation from those assumptions is something that you'll deal with way later in your chemistry career. For right now, all you need to do is know this equation and how to deal with it. Okay. The ideal gas equation is this PV equals nRT. And that is something that you guys should just have embedded in your brain. PV equals nRT. Go ahead and chant it to yourself 100 times. Have it memorized. PV equals nRT. It's something that you're going to be expected to know. Usually we don't make you memorize equations and stuff like that. Ideal gas law is an exception. It is just something that you absolutely have to know, right? So PV equals nRT. And if we want to go through, what are each of these? So the P stands for the pressure of the gas. Okay. V stands for the volume of the gas. N is the number of moles of gaseous molecules. Number of moles. And I'm going to skip R for a second and go to just T. T is the temperature of the gas. Okay, and importantly, as I kind of prefaced before, anytime we're talking about gases, the temperature has to be in Kelvin. Volume is usually in liters, pressure is usually in ATM, but we could talk about volume in anything we want. We could talk about pressure in any unit we wanted. Temperature has to be in Kelvin, right? So it might be volume in milliliters or centimeters cubed or liters or whatever a volume measurement is. Temperature is always Kelvin. Likewise, pressure might be torr, it might be ATM, it might be pascals. Temperature is always in Kelvin. So this is something that's really, really, really important that you guys know. It's a #1 sticking point because a lot of problems will say the temperature of the gas is 25 degrees Celsius. You have to know, because this is a gas problem, the first step is to convert it to Kelvin. All right, so mark my words, the easiest mistake that y'all can make in this is to not convert the temperature to Kelvin. That's a really key component, okay? So these are the 4 variables of this equation. So just like any math problem, if I gave you any 3 of them, you'd be able to find the 4th. So if I gave you volume, pressure, and number of moles, you'd be able to find temperature. If I gave you temperature, number of moles, volume, you'd be able to find pressure, et cetera, et cetera. These are our 4 variables. The R is kind of weird in that it is what's called an ideal gas constant. It's a constant. It's just a set number. It's not a variable. You'll never like solve for R or anything like that. It's just a constant number. The value of R actually depends on what your units you're talking about. So here are the values given for the units: liters, ATM per Kelvin mole. If we look at our constants page, and this is what we're really going to use, so let's not even bother with what was given there. Let me get rid of all those. We go to our constants page. Here are the ideal gas constants that are given. Okay, so this one here, which is in units of ATM, or liter ATM per mole Kelvin. There is another one that's given, and the difference here is that the units of pressure are torr, not ATL, or ATM rather. If you converted from torr to ATM, from ATM to torr, from atmospheric pressure to torr, or vice versa, you would be able to convert between these 2 numbers. So they look like different numbers, but really the only difference is the units being used. So what you want to do is make sure to pay attention to the units of pressure that are being asked for in the problem. That'll dictate which one of these 2 you use. There's this other one here. We're not going to bother with that one. Don't get too bogged down on that. That's for a little bit more of an advanced class. Okay, so these 2 ones here, the one in orange, which is again talking about pressure in terms of atmospheres or ATM, or the blue one, which is talking about pressure in terms of torr. These are the ideal gas constants. And again, you could convert between the two of them. You could convince yourself right now by punching this into your calculator, but you could convert between the two of them using our pressure conversion factors we talked about, or you just trust me that the difference is the units of pressure that are being used. Okay, truth be told, this is going to be the one that you use more often, the 0.02058. One thing I will note is just like every single thing on this constants page, I'm going to expect you to carry every single digit. So you're not going to randomly round it off. You're always going to be punching 0.082058 into your calculator. Please do not just randomly round. Always give all the digits that are given to you, right? We love our significant figures. Okay, so again, our ideal gas equation consists of 4 variables: pressure, volume, number of moles, and temperature, and then this ideal gas constant R. Okay, so that means that if you know the pressure of the gas, the volume of the gas, and the number of moles, you can calculate what the temperature of that gas is. Or if you know the volume and the number of moles and the temperature, you know the pressure of that gas, right? So that's the relationship between these 4 quantities in this ideal gas equation, which is pretty cool. I mean, I kind of understand that at the early stages of chemistry, this doesn't sound like it's the coolest thing in the world, but being able to relate these 4 fairly different quantities in one equation is something that's quite powerful. So now let's use our ideal gas equation in a bunch of different calculations here. Okay, so we're going to calculate the volume of 1 mole of ideal gas at room temperature, which is about 25.00 degrees Celsius, and 1 atm. So first of all, what is the ideal gas equation? P V equals N R T. You just got to know it. Second step with these problems is, what is your unknown? So in this case, it's asking us to calculate the volume. So the volume is going to be our unknown variable, which means that the number of moles is given, right? We have the number of moles, we have the temperature, we have the pressure, and we always have R, because R is a constant. We always just look R up from that constants page. So what I'm going to do is I'm going to take this equation and rearrange it to solve for volume, which means that I need to divide both sides by pressure. Over here on the left, the pressure will cancel out. And so I'll be left with a new equation: volume equals nRT divided by P. If that type of algebra is uncomfortable to you, you want to get good at it, right? Being able to arrange it. It's not a very complicated equation because it's all just multiplication. So you need to be able to arrange that equation very easily. So what I would recommend is, in this case, we just solved it for volume, rather, for V. Take a second and solve it for P. Take a second and solve it for N. Take a second and solve it for T, right? You want to be able to rearrange this equation and solve for any one of those 4 variables, because that's what these problems are going to be. I'm going to give you 3 of them. One of the 4 is going to be missing. Okay. All right. So then we're just going to take this and we're going to plug in everything that we know. So volume equals N, number of moles. So let me actually color code here. N is the number of moles, so that's 1.00 moles. Put it in parentheses. R, where do we get R from? That is from our constants page. Which one of these 2 values do I use? I'm going to look at the units for pressure. So I'm going to go back and I'm going to notice that my pressure units are atm. So that tells me that I need to use this top one here. This is going to be the value for R that I use. So 0.082058. .0082058. Hopefully that's what I said. And then the units are liters times atm divided by moles Kelvin. And these are just about as ugly a unit as you can get. But we're going to see that it's really important and it's going to help us keep track of our unit. Just like everything else we've done, our units are going to cancel and we're going to be left with units of volume, which in this case will be liters. So I'll show you that when we get to it, but trust me on that. That's why these sort of exist. I can anticipate I'm going to run out of room. So let me start moving stuff up. Okay, and then the temperature is 25.0 degrees Celsius, 25.00 degrees Celsius. But what did we say about, let me just real quickly color code, temperature. But what do we say we're going to always have to do, because this is an ideal gas problem? First, we have to convert that to Kelvin. So if we don't remember how to do that, that is on our constants page here. But you just take the temperature in degrees Celsius and add 273.15. Okay, so we're going to take this and add 273.15, and that will give us our temperature in Kelvin, which in this case would be 298.15. Because of the rules, so first of all, the 273.15 is exact, but I still have to keep track of my sig figs for temperature. So I'm going to have to mark here. So my 298.15 Kelvin, even though that number as written does have the correct number of sig figs, I'm going to mark it because it wouldn't always. If, for example, it was just 25 instead of 25.00, I would need to have the correct sig fig marked. We'll do an example where that's the case so you can see what I'm talking about, but just trust me that it's important to keep it marked. Remember that we don't round anything until the very end. So anyways, just trust me, keep it marked. We know that that number actually has 5 sig figs. And then we're going to divide by a pressure of 1.00 atm. Okay. So now that I have it all set up, I'm just going to punch it into my calculator. I recommend, just like before, I recommend you follow along, punch this into your calculator, and make sure you get the same thing on the other side that I do. If not, that just means that there was an error, something went wrong when you punched it into your calculator. So 1 times 0.082058 times 298.15 divided by 1, you should get 24.465. 4655. Okay. All right. We'll worry about sig figs here in a second. The first thing, or the next thing rather, that we're going to do is units. Okay. And everything's going to be all canceling out with the units of R, right? So moles is on top here, but then dividing by moles in R. Kelvin divided by Kelvin, and then ATM divided by ATM. So notice that we're left with liters, which is awesome because that's what we want, is units of volume. Now we can go back and figure out sig figs. I'll use orange for our sig figs. There's 3 in this number. This number is not exact, but it has 5. That's why we always carry all those digits so that it doesn't limit our sig figs. And then our temperature also has 5, and then our pressure has 3. And fortunately, since this is just a big, ugly multiplication and division problem, all we do is take whichever one has the fewest number. In this case, that's 3. So our final answer would be 24.5 liters. Okay. So yeah, I was given, and I didn't quite do a good job of following it up color coding. I was given 3 variables, number of moles, temperature, and pressure, and I solved for that 4th variable, which was volume. So we're just going to do an example of each individual variable missing. First thing we're always going to do is start with our ideal gas equation. PV equals nRT. Again, you just want to have that memorized. It says calculate the pressure of 1.44 moles of an ideal gas at 5.00 liters in a container that's at 36 degrees Celsius. Okay, So what's my variable? My variable is pressure. So that means I need to isolate this. So I'm going to do that by dividing by volume on both sides. It'll cancel out over here. So if I just kind of rearrange to make it look prettier, I have P equals nRT divided by V. Okay. Before I even get going here, I'm just going to note that my temperature is in Celsius. What's the problem with that? This is a gas problem, so it has to be in Kelvin. I'm going to just take my 36 degrees Celsius. I'm going to add the 273.1, whoops, 0.15. Well, hold up. That was ugly. The 273.15. Add those together and I'll get my answer in Kelvin. That would be 309.15 Kelvin. But my sig fig is in that ones place. Again, this quantity here is exact, so I'm just going to completely ignore it when I calculate sig figs. And that means that my last sig fig is the 9. Okay, so this number here has 3 sig figs. When I go to use it in this problem, I'm still going to carry all of those digits. I'm not going to round until the very end. So that's why we're going to make sure to leave it marked. Okay, so now let's plug in all of our other variables. N is 1.44 moles times R. Let me color code here. So N is the 1.44 moles. I need R, which again, I'm going to get from the constants page. We're going to take this first value here. We're actually going to do an example with both of them, but I just want to make a point. So let's take the first value, the 0.082058. So this, whoops. And those units were ATM, liter per mole, Kelvin. And then times our 309.15 Kelvin with that last sig fig marked, divided by the volume, which was 5.00 liters. All right, punch that into the calculator, and what you're going to get on the other side is 7.30605. All right, then we're going to do units. Again, moles will cancel with the units of R. Kelvin cancel with the units of R, and now liters do. So we see that we're left with a pressure in units of ATM. If we go back and do sig figs, now we're going to count sig figs. It's all a multiplication division problem, so that's kind of best case scenario with sig figs. I have 3. This, because I've marked that 9, this only has 3. And my volume has 3 as well. So that means that my final answer should be reported to 3 sig figs. So pressure is 7.31 ATM. Okay, again, I was given my variables of, what hasn't been used? I was given number of moles is 1.44. R, we always know from the constants page. T was 36 degrees Celsius, which I then converted to Kelvin. And then the volume was 5 liters. So I had my 3 variables and I used it to solve for the 4th. Okay, so now let's just see, kind of going back here, what's going to happen if instead of using the value for R that I decided to pick, what if I use the different values? So instead of using this one, I'm going to use this one, 62.36 liters torr per mole Kelvin. Let's say 236. Oops. Liters torr per mole Kelvin. Now when I punch this into my calculator, I'm going to get 552.23. And then when I go to figure out my units, moles will cancel, Kelvin will cancel, liters will cancel, and I'll be left with torr. So again, you can see that the only difference between these two values for R is that I'm left with different units for pressure. So that's how you know which one to pick. You're going to look at the units for pressure. In this case, I could have done either because I didn't specify which units I wanted for pressure. So either one of those would have been acceptable. Usually the problem would say something like calculate pressure in torr or calculate pressure in ATM. But let's say it was an exam and I forgot to specify, either one of these would be perfectly acceptable. So then sig figs, we have 3, 4, 3, and 3. So our final answer should have 3. So that's 5,550 torr is the pressure. Right, and again, you could sort of convince yourself that if you converted 5,550 torr to ATM, you would have gotten the same answer as we got in the previous. All right, so now we're gonna solve another problem, but in this case, the unknown is the number of moles of the ideal gas. So PV equals nRT, but we want to solve for number of moles, or N. So we need to isolate N. So we're going to divide both sides by RT. So on the right side now, R will cancel and T will cancel. And so we're left with N equals PV over RT. I'll move this over here just because that's kind of the way that we're used to looking at it, although it doesn't really matter. So by taking my ideal gas equation and rearranging it, I got N equals PV over RT. The pressure, and I do want to note that I've done a little bit of a different example than what was on the books given lecture slides, just so we can go do examples with a different number of sig figs, because for whatever reason, the book loves to pick 3 sig figs. It's not always going to be 3 sig figs. So let's make sure we know how to do it when it's not 3 sig figs. All right, so I'm going to start plugging in pressure 1.800 atm times the volume, which is 12.30 liters, right? That's my volume. And here, actually, the temperature is given in Kelvin, so I don't have to do any other work with that, which is nice. 298.0 Kelvin times R. So I want you to take a look at our constants page real quick and tell me which value of R you should use. So this is the temperature. Which value of R would be the correct one on our constants page here? Okay, so again, looking at the problem, the pressure is given in ATM. So that means I'm going to need to use this value here, which has the pressure units in ATM. Oops. And I'm putting these in parentheses all the time to get you guys in the habit of doing that for when you punch it into your calculator, because that's a really easy mistake to make. Actually, in particular, when you're going to punch this into your calculator, this is a really important problem to follow along to make sure you do it correctly. This whole thing on the bottom here needs to be in one set of parentheses, because you want to divide by that whole thing. If you don't put it in parentheses, you'll end up dividing by R and then multiplying the whole thing by T, not dividing by T. Okay, so punch this into your calculator and see what you get. What I get is 0.905399,998, something like that. Okay. What's the next step? Units. So I have ATM on the top. I'm dividing by ATM. Liters dividing by liters. Kelvin dividing by Kelvin. And so what I'm left with is 1 over mole. And this is just equal to mole. Okay. This is just sort of like basic algebra. 1 divided by 1/2 equals 2. Like you hopefully that's something that's familiar to you. If not, you want to just review fractions in algebra. But yeah, that's how I got that equation there. It's nothing sort of fancy. It's just basic rules of algebra. All right, and then for sig figs, I have 4 sig figs for my pressure, 4 for my volume, 4 for my temperature, and then what is that, 5 for R. So that means my final answer should have 4. So 0.9054 moles of gas. That would be my final answer. Okay. Last problem we can do is missing that last variable we haven't talked about yet, which would be temperature. And luckily it wants it in Kelvin, so that's not as hard, as pain in the butt of a problem if it had asked for it in Celsius, but you know, you could maybe convert this to Celsius at the end just to convince yourself. I'll go ahead and do that. So step 1 is as it always is, PV equals nRT, and you're going to identify the fact that you want to solve for the temperature in Kelvin. So it means I'm going to divide both sides by NR. N cancels and R cancels on the right side. So if I just kind of rearrange this to make it look pretty, I get temperature is equal to PV divided by NR. Okay, so that's what I'm solving for here. Just starting to fill in here. Pressure. It says that the pressure is standard pressure. So this is something that we haven't seen before. So let me just say standard pressure equals 1 ATM exactly, meaning that it's not going to limit your sig figs. So what I'm going to do is I'm going to write 1 ATM. But again, this is standard pressure, so I know that even though I've only sort of written this number as 1 sig fig, because it's an exact number, I know it's not going to limit my sig figs. I'm not even going to pay attention to it when I go to figure out sig figs. Times the volume, that's 30 liters, 30.00 liters, divided by the number of moles, which is 2.71 moles, times R. All right, so everybody take a look at your constants page and tell me which value of R we should be using. Again, it has everything to do with the units of pressure, which is, again, ATM, and it will be in most cases. Just don't get too complacent with that and make sure you're watching out for the rare occasion that it's actually torr. So 0.08205 ATM liters per mole Kelvin. Again, when you're punching this into your calculator, this bottom thing, you have to put that whole thing in parentheses. Punching this into my calculator, I'm going to get 134.9059. Should be in units of Kelvin. That's what we were asking for, but let's just make sure. ATM cancels, liters cancel, moles cancel, and just like before, I'm left with 1 over Kelvin, which is just Kelvin. Okay. Going back and looking at sig figs, this is exact, so I'm not going to pay attention to it. my 30, oh, sorry, should have been just 30.0. So that's 3 sig figs. There are 3 sig figs here and 5 here. So my final answer should have 3 sig figs. So that's 135 Kelvin. All right, so now what if instead I wanted to make this problem a little bit more complicated and I asked for the pressure in units of Celsius instead of Kelvin? Now we're going to have to add one more step onto this where we take our 135 degrees Kelvin and use our conversion factor, which is now down here, where I can convert from Kelvin to Celsius. So Kelvin equals Celsius plus 273.15. If I want to go the other direction, that means that Kelvin minus 273.15 is equal to Celsius. So that's what I'm going to have to do. I'm going to have to take my 135 and I'm going to subtract. And actually, you know what I'm going to do to be extra good is I'm going to take my unrounded answer, 134.9059, with the sig fig marked and subtract 273.15. Right? You always want to round at the very last step. So you shouldn't be doing any calculations with rounded numbers. So I'm actually going to take this number here before it was rounded with my sig fig marked and use that in my calculation. So I know that I'm still going to have to round to the ones place at the end, but negative 138.24 degrees Celsius. So negative 138 degrees Celsius, that would be my final answer in Celsius.